Okay, good morning, everyone. I think this is where we left off. Um, Here, talking about the wave theory of light, because as we know, in modern times now we have this dual theory of both waves and particles. But here in 1800, it was established that the fundamental behaviors of light could be explained by waves. And one that particles couldn't do was the interference of light. So we will be working with the wave theory of light for the rest of our discussion. And I think this is where we were. We were talking about the different, kind of the anatomy of a wave. And we have crests and troughs. We have the wavelength from a crest to a crest. We have the amplitude of the wave, and finally, this notion of frequency, low frequencies and high frequencies. And if you're talking about a wave that's moving at a constant speed, and we will be, we're talking about light that's moving through space or through air when it gets through our atmosphere, but the speed does not change appreciably at all. The speed of light in a vacuum and the speed of light in air is virtually the same. So as long as we're talking about a wave moving at the constant speed, then there's a nice relationship between frequency and wavelength. Okay, you can talk about one or the other. They're equivalent descriptions. Realizing though that low frequencies correspond to a very long wavelength, and a very high frequency corresponds to a very short wavelength. Astronomers tend to talk about wavelengths, and physicists tend to talk more about frequency. So we're going to be talking mostly in the language of wavelengths, and hardly refer to the frequency at all. But just remember, there is this very simple relationship between the two. When you know the wavelength of a wave, you can immediately, if you want to, calculate the frequency and vice versa. But we're going to stick to our wavelength description of light, so we can kind of have it more or less fixed in our mind. Okay, so we're back, as we seem to always. We're back to Herschel. He made a fascinating experiment. He was interested in the different colors of light when you break up sunlight into colors, and everyone was interested in the different brightnesses of the colors. Are they all the same brightness? And turns out no. We'll see a couple of graphs in a minute about how the different brightnesses change. The different colors have different brightnesses. But he made a very interesting experiment. One of the ways to get after brightness, he thought, was to see what kind of effect the different colors would have on a thermometer. The idea being, the brighter the light, the greater it would heat up the thermometer, and he would take a look at the effect of the different colors on a standard thermometer. And he went ahead and did that. And there's the picture there of him with his colors and his thermometers. And he just did what great scientists do. He put a thermometer beyond the red and beyond the violet. And to his surprise, when he put a thermometer beyond the red color, the thermometer reacted more than any other color. That is, that thermometer warmed up quicker and to a higher temperature than any of the other colors. So naturally, because he was thinking in terms of this heat was being produced by the light, that this was clearly an invisible ray. You could not see this light. So he called it caloric rays, for heat rays. And of course, we now call it infrared rays. And infrared astronomy has become a very, very important part of our arsenal, in which we have telescopes just dedicated to the infrared region, those great enormous discs that you see. I think the biggest one, is in Mexico. They are all infrared telescopes, because the wavelength is larger. You want to use a larger aperture, so you need these very, very great discs. But an infrared telescope was sent up into space, and since astronomers, as we know, love their history and know their history, they called it the Herschel Space Observatory. It was up working from 2009 to 13, and it was the first telescope camera devoted to the infrared region of the sky, a region which is invisible to our eye. Not to be outdone, the next year, a German chemist by the name of Johann Ritter was interested in the other side of the spectrum beyond the violet. The thermometers didn't do very much on the violet side, so he had the idea of using something more sensitive. He used what we would call now a rudimentary photographic paper, paper kind of dipped in this silver chloride solution, in which again the different colors would change, would chemically react. The light would chemically react with the paper, and it would by and large make the paper turn dark. And so the darker the paper turned, the more energy was going in through that color. And of course, giving the hint from Herschel, he went ahead and was very interested in what would happen to the paper on the other extreme side, on the violet side. And just as with Herschel, he found that the paper got darker on the extreme of the ultraviolet side than on any other color. So whatever these rays were, they were not the caloric rays, because the caloric rays did not do a very good job in turning this paper dark. The red and the infrared, now that we knew about, did not do much to the paper. But the other side, as we moved towards the green and the blue and the violet, and the paper got darker and darker, this extreme side, these, again, rays, invisible rays, interacted more strongly with the silver chloride than any other color. I don't know if he gave those a name. I don't recall, but of course, we now call this ultraviolet light. And so we have a broadening of the spectrum here. Around the same year that Young established the wave model, we now begin to understand that the wavelengths of light are beyond just the visible spectrum that we see. Visible light begins in the violet at 400 nanometers. That's 400 billionths of a meter. Yeah, you heard that right. It's just a billionth of a meter. The wavelength here from crest to crest for visible light is very, very small. And it goes up to 700 nanometers, 700 billionths of a meter. And just to give you an idea of what that would translate into frequency, if we took green light, something in the middle of 500 nanometers, you're talking about 600 trillion cycles per second. So if you were watching green light go by you, and you wanted to count how many crests went by you in 1 second, you'd have to be prepared to count 600 trillion of those crests would go by you in 1 second as the light passed you by. Or it simply would undulate up and down from crest to trough to crest, that full cycle. 600 trillion of those cycles would go through for green light. So the most important white light for us, of course, is the sun, by far. And people were very interested in studying that sunlight moving forward from Newton's great experiment of, first of all, dispersing the light into colors, showing that those colors could be brought back to white light. But there was tremendous interest in this composition of the colors of sunlight. And one of the simplest questions you could ask, if you think about it, is, well, what are the different brightnesses? Are all the colors coming from the sun, it's the whole spectrum, from red all the way up to violet, do they all have the same brightness? And it turns out no. As a matter of fact, we could even ask more now that we know about the infrared rays and the ultraviolet rays. Do they all have the same brightness? And the answer is a resounding no. It was found, here's a crude graph, bar graph. It was found early on that, in fact, the brightest light from the sun was coming from the green-yellow region. And the red was still pretty bright. It didn't fall off very dramatically on one side, but the other side, it did. The blue was less, and the violet was much less. So that we found that sunlight peaks in that green yellowish band, the brightest that the light color that the sun is actually giving off. Here's a more detailed look. It's more of a modern look. This is not something that was understood very well in 1800. But what you're looking at here, the color okay, the color graph that you're looking at is an accurate spectrum of sunlight. Okay, don't worry about the black line for a moment, the smooth black line. If you take a look at that, you can see that sunlight does peak in the visible region. Of course, that's the opposite. That should be said in the opposite way. Because the sun peaks in this region of wavelengths, it is visible to us. Our eyes and the eyes of most animals here on Earth have adapted themselves to see the brightest light coming from the sun. That's why, that's why it's the visible region, not the other way around. And you can see there is light coming from the sun, from the ultraviolet region of the spectrum, and there's plenty of light coming from the infrared. And as we know, there are some animals, insects particularly, can see this part of the spectrum. I think famously bees, I think, can see ultraviolet light, and there are other species which can detect infrared light. You can see it's a little bit jagged there. The chemistry of what the nuclear chemistry, I guess would be the proper way to describe that, of the sun is rather complex, as you can imagine. So it's not a completely smooth spectrum that's coming out. It is a little bit jagged, as you can see. What the black line is what a theoretical, just simple hot body that is glowing at different temperatures. Different temperatures will give you different of these black graphs. And this is about the best temperature. This temperature kind of covers what we see of this visible spectrum as best as possible. This is the best fit mathematically. And so a body that is heated to 5,525 degrees Kelvin would give off a spectrum, theoretically, give off a spectrum of colors in the same general distribution as we see in the sun. And this is, once this is studied more in great detail, and the theory is understood of why the color spectrum for different temperatures are this way, we now see we will begin to be able to measure what the temperature of things are just by looking at their spectrum. So we're beginning to get a notion that the spectrum is starting to tell us interesting things about the body that's giving off that light. But here's maybe a more interesting picture here. This is what, in the red, this is the spectrum, this is the brightness here on Earth, where we are on the surface of the Earth. The yellow is exactly the same as the colored spectrum that we saw just a moment ago. It's the same graph. Okay, it's just all in yellow, just seeing the different brightnesses. You can see though the red is just what brightnesses survive as it goes through our atmosphere. And you can see they're all depressed. The atmosphere absorbs some of the brightness of all the colors, but certainly not uniformly. For example, here down in the infrared region, there are parts of the infrared which get through completely. It's exactly the same as the amount of energy that's coming down above the atmosphere. But then again, there are other parts, which we call the absorption bands or the absorption windows, in which none of this infrared light gets down to the surface, where it's just completely absorbed. It's absorbed mostly by the water vapor in the air, a little bit of the CO2 in the air. So for example, if you wanted to build a telescope that was going to study this part of the infrared spectrum, you're out of luck if you want to build it on the Earth. None of those rays are getting through. If you want to see these infrared rays, you've got to put this into a balloon, which was done in the early days, and finally now into a space mission, orbiting the Earth above the atmosphere to see any of the light coming in this part of the infrared spectrum. Take a look at the other side. You can see there's plenty of ultraviolet light that's coming from the sun. But look what a good job the atmosphere does in cutting that ultraviolet light down, okay? From the yellow down to the red is quite dramatic. And you see the ozone 3 there, O3, that is what is absorbing so much of the ultraviolet light. So just a very little bit of ultraviolet light actually gets down to us on the surface thanks to the ozone layer. You remember the great problem we had back in our youth when the ozone layer was disappearing. and how the world got together to fix that problem. But this is the part of the spectrum that will give you a sunburn, right? And it'll give you a sunburn on a cloudy day, okay? Because it goes right through the atmosphere, and this will go through even though the visible light is being blocked, being scattered very much on a cloudy day. So this is a very interesting graph to see the comparison of the yellow, which is what the sun is giving off in this part of the spectrum, from the ultraviolet down to the infrared, and what actually reaches the Earth. So in studying the solar spectrum, which looks like a very pretty rainbow, our friend Fraunhofer, you remember Fraunhofer, the great telescope builder of his day in the 1820s. He, of course, had the most magnificent lenses and the most magnificent prisms. And so he took one of his great pieces of glass and broke up the spectrum, spread it out in about the best way possible. And then he did a very smart thing. He took one of his telescopes, okay, in the lab, okay, and he looked at the spectrum through the telescope to really see the detail, to look up real close at this very, very broad spectrum that he created with his wonderful prism. And to his surprise, what he saw was this. He saw these dark lines, many, many dark lines in the spectrum of the sun. Of course, all the colors were there, and you could even see the graph up on top. The graph here up on top is the different brightnesses, and we can see that he saw that the brightness peaked in that yellow-green region and fell off towards the violet and fell off towards the red. Actually doesn't fall off to the red as dramatically as he was able to ascertain at the time, but he did get the peak. He did see where the spectrum was at its brightest, and he saw 576 dark lines, and he drew them all meticulously. At least he drew 100 or 200 of those meticulously, where they were in the position of his spectrum. And some of the lines were more prominent than others, and he gave them names, letter numbers, which have become very famous. They are still used today. You can see A, B, C, D, E, the Fraunhofer lines. But of course, he and no one else had any idea what these dark lines were doing in the sun spectrum, in this beautiful color spectrum. Where were these missing colors? What happened to these missing colors? There should be colors there, but yet no color was there. It was a region of darkness in the spectrum. Was the atmosphere just absorbing these colors, or what was going on? He had no answer for that. But clearly a very important open question at the time to try to explain the dark lines of the spectrum of the white light of the sun. That was solved in the 1850s, 1860s by a great pair of scientists, Kirchhoff and Bunsen. Robert Bunsen, the chemist of Bunsen burner fame of our chemistry labs of old, and Kirchhoff was a physicist. So it was a great team of a physicist and a chemist. They worked together in the same university, and they began a serious study of spectra. They started with the simplest element, hydrogen, and it turns out when you take hydrogen gas and make it glow, make it hot, now the easiest way is to put it into a fluorescent tube filled with hydrogen. Of course, they weren't able to do that at the time. They had other means of making the gas get excited so it would glow. And when you do that with hydrogen gas, it gives off this very pretty pink color. Yeah. But when you analyze that light and see what are the colors of that light, is it just one light of pink color? No, indeed not. When you put this light through a spectrum, through a prism, what you get are these 4 bands of color. The red is very predominant, and it is the brightest, and then there's a green band and 2 violet bands. These are the only 4 colors that hydrogen is producing when it's exciting. And to our eye, this mixture of these 4 colors with the brightnesses that they have turns into, in our brain, this particular pretty color of a pink rose. Again, what's going on here, guys, is not complicated as a concept. You have the glowing light here. It's sent through a slit so that it could be put through a prism, and you simply break up that light, just the way Newton did for white light. just as Fraunhofer did with white light. But when you break up this pink rose light, you don't get the continuous spectrum. You get just 4 colors. And this is the hydrogen spectrum, the most important and the most famous spectrum in the universe. As we know, at least 90% of the universe is made of hydrogen. So this was the beginning of a serious study of what spectra was. And they didn't know why hydrogen gave off these 4 colors and no other colors, but at least they were beginning to catalog what different elements gave off in terms of their spectrum by making them glow. And here's an early set of spectrum that was developed by Kirchhoff and Bunsen. Very important one. Here's our hydrogen here, right? Here's that red, green, and 2 violets. Here's a very important spectrum of sodium. Okay, we have this very, very strong double yellow line here. There are 2 sets of double lines, but this particular line is these 2 particular lines are very, very bright. They overwhelm the other 3 or 4 or 5 lines in the sodium spectrum. I think you can remember from chemistry the cool thing of putting salt, simple table salt, into the Bunsen burner. You put it on a little bit of a metal wire and put the salt into the Bunsen burner to the hottest spot. It would glow that beautiful yellow color. Okay, that's what it looks like to our eye because it's these 2 yellow bands here coming from the sodium spectrum, which dominate the color of the sodium. So when you use salt, sodium chloride, you will get the spectrum of sodium. You can see they're very complicated. Here's calcium, magnesium, here's neon. Okay, and if you have a fluorescent tube of neon, these will be the brightest colors down here. The blue and the yellow, they're there in the light, but they're relatively dim, and so a neon light will be mostly most of the brightness will be coming from the red, and so we get our well-known neon colored light. This was used to great advantage by Kirchhoff and Bunsen. They actually used it as a tool of discovery. They began going through all their minerals that they had in the lab and just checking out the spectrum. This, of course, is before the time of easy photography. These spectrums had to be studied, put up onto a wall, onto a mat, and drawn. And sure enough, there were some minerals, some things in their cabinet of materials which had no known spectrum. And here are 2 early ones. In 1860, here's a spectrum of cesium. They named that after the beautiful blue color that it gives off. And a year later, they discovered another element that they could not find a spectrum for, a new element, rubidium, named after its beautiful red color. And so here is the spectrum of rubidium and cesium. And again, they would create this spectrum. They would draw it very, very carefully, and they would simply compare this to the catalog of all the other spectrums that they had. And this did not match up to anything. And so here was a new tool that the chemists had to discover new elements in the periodic table by looking at spectra. And here's the catalog of the complete spectra today. It even goes beyond uranium. It even goes into the elements, the artificially made elements. Here's plutonium here, for example. So every element, whether it's naturally made or even artificially made, is after all constructed by neutrons, protons, and electrons, and somehow or other, that combination is giving off these particular colors for the different configurations of the atoms. Then no one knew why, but they certainly could make a catalog of it and be used very, very effectively to identify spectra, unknown spectra of things that they were studying about. But undoubtedly, the most important discovery that Kirchhoff and Bunsen made was for the absorption spectra. This was done in 1859, and very often it's compared to Darwin's great work of the same year, The Origin of Species. This is a discovery on the same order of importance in astronomy, in astrophysics, as Darwin's great work in evolution. This discovery of the absorption spectrum really revolutionizes our ability to study the stars. Let's go back and just review for a minute. If you have a hot body which is glowing, generally it'll glow a nice, beautiful, continuous spectrum, like the sun, like a light bulb. For example, if you have a hot poker, it'll start to, and it gets hotter and hotter, it'll first of all burn red. It'll be red hot, then it can get orange hot, right? As the colors change, and finally it'll get so hot that it'll glow white hot. All the colors will be given off as the temperature gets higher and higher. Well, that's fine. That's a continuous spectrum. If you have one particular element or one or two elements that are glowing, get them to be excited in some way. The easiest way to conceptualize it is to make it very, very hot. So we can keep that as a simple idea of why something would glow. There are other reasons why we can do that. For example, sending an electric charge through it for a fluorescent light, but we'll just keep things simple in our mind to make the element glow. It'll give off these emission spectra. Okay, they will not give off a continuous spectrum. They will not look white. It's not white light that's coming off. Okay, for hydrogen, it's coming off that very pretty pink rose color. It's not white at all. So here would be the emission spectra of a particular element, and these can be cataloged. Okay. What they discovered was they took that white light, the light that was giving off all the colors, and they sent that light through the very same cool gas that the hot gas would give off this emission spectra. What the cool gas would do is the cool gas would absorb the very colors from the full color spectrum that the hot gas would give off. This was just remarkable. In other words, what they found was that you could actually get a negative image of the emission spectra by sending all the colors being created by a hot body giving off white light through the cool version of the gas. That gas would absorb the very colors that it gives off when it's very, very hot. Okay, I see I've got a couple of questions here. I am breaking up. Okay. Yeah, what I'm going to do, guys, is I'm going to turn my other screen off. I'm going to, thank you for telling me. I'm going to kill this if I can. I've always had a second screen up so I can see what you guys are seeing. Okay, I'm going to leave this. So this will free up some bandwidth. Hopefully that will improve things. And I think I'll still see a chat if a new chat comes on. So if I'm still breaking up, then let me know. But hopefully that will help. You might see in my background, I'm in a different place. I'm not where I've been all these many weeks. I'm over in another place in my house, and so the signal apparently is not as strong. So hopefully we can muddle through this last class. Hopefully I'm not breaking up too much. Okay, so let me see. Much better. Good, thank you, Becky. All right, much better. Yeah, I just closed down my other screen, so I'm not taxing the bandwidth here at the house as I was. All right, great. So back to this great discovery of the absorption spectra. This will play such an important role in the rest of our presentation. Let me say again what's going on here. You take a body, a hot body, which is glowing all the colors, what we call white light, and you send that white light through a cool version of a gas that you know, for example, the spectrum of, like hydrogen or oxygen. And what the cool gas will do, it will absorb colors. Again, they did not know why these things were going on. There was no explanation here. Okay, they were just this was just empirical discoveries that were being made. So what the cool gas would do is literally absorb the very colors that when the gas was glowing, it would give off. And so the absorption spectrum is a mirror image of the emission spectrum. And when they saw an absorption spectrum, when they saw a white light, beautiful color spectrum with dark lines in it, they said, aha, is this what's going on with the sun? Are these the dark lines of the sun? Of course, when you're just looking at hydrogen, if only hydrogen is absorbing the light, then you'll only get 4 dark lines. The sun had hundreds of dark lines. But they said, well, is this what's going on? Are there many, many elements, somehow or other, absorbing all kinds of the colors coming from the great white light of the sun? And that's what we see in these dark lines of the sun. Certainly, it made a lot of sense. And this was the idea that the sun was creating white light, to be sure. It was creating all the colors, as we saw in that graph. Okay, but is there some layer of the sun, some atmosphere, some, say, a gas of the sun that was absorbing some of the colors as it was being released out? And that is exactly what is going on. That is exactly the correct explanation. This layer is called a photosphere. It's very, very thin skin. It is actually what we see. When you see a picture of the sun, what you're looking at is the photosphere. It's very, very thin layer, about 50 kilometers wide. And it does have the ability, depending upon what's in the photosphere, what elements are in this photosphere, to absorb some of these colors in these absorption spectrum. And you know, when they began to take spectra of, when these prisms were sensitive enough that you could take spectra of other bright objects, the moon and Venus being the 2 brightest objects in the sky after the sun, they saw that the spectra of the light coming from the moon and Venus was exactly the same as the sun spectra, had the same dark lines. So clear proof that what we were looking at, when you're looking at the light of Venus and the light of the moon, you're looking at sunlight. Okay, that light is coming from the sun, bouncing off of the moon, and coming to our eye. We are looking at just simply reflected sunlight. Okay, so people began to look at the Fraunhofer lines now in a completely new light. By 1862, there were many, many spectra. You could look up in the catalog of many, many spectra of elements. And what was the most prominent of the lights of the lines that could be seen? Of course, hydrogen would be the most prominent, since the sun is 90% hydrogen. And I think the sun is more than 90% hydrogen. On average, the hydrogen is 90% of the universe. I think the sun could be more like 95 or 96% hydrogen. And so in looking at here is the spectra of hydrogen. Here's the great red line. Well, that turned out to be Fraunhofer's C line. And the beautiful blue-green line turned out to be Fraunhofer's F line, lines that he saw right away in 1815, how prominent these dark lines were. 2 very interesting lines in the yellow. Yes, remember? Yeah, remember those 2 very, very bright lines in the sodium spectrum? Yeah, Fraunhofer marked those as 2D lines. I think he called them DA and DB, I believe. And here are the other 2 colors of the hydrogen spectrum. Again, they were lines, less prominent lines, because they're not as bright in the hydrogen spectrum. And so they were marked by Fraunhofer, but weren't given full letter lines. And so in 1862, Angstrom was able to establish beyond doubt that yes, the 4 emission lines of hydrogen were in the absorption spectra of the sun. And so yes, hydrogen is at least in the photosphere of the sun, which was established in 1862. And this was remarkable. I mean, think about it. We now are talking about what are the chemical elements that are in the sun. Who would believe it? Who would ever think so? Well, very famously, you may have come across this quote in your other readings in history of science. The famous philosopher of the time, Auguste Comte, wrote very famously about the stars. He said, "We conceive the possibility of determining their forms, their distances, their magnitudes, their movements, but we can never, by any means, investigate their chemical composition or the mineralogical structure, much less the nature of the organic beings that live on their surface. Remember, this is a very common idea in the middle of the 19th century. It goes all the way back to Herschel, that there were definitely beings, there were definitely alien beings living in other places on the universe. A very, very common idea that was lost for a while, but had quite prominence among serious thinkers at the time. In short, to put the matter in scientific terms, the positive knowledge we can have of the stars is limited solely to their geometrical and mechanical phenomenon. And we can never be extended by physical, chemical, physiological, or social research, such as we can be expended on entities which are accessible to all our different means of observation. So this was made, I think, the year before chemical composition of the sun, and very, very quickly the stars were beginning to be made. One of the great bad prognostications in the history of science. So going back to the Fraunhofer lines, yes, now they began to be identified. These great lines here, as Fraunhofer labeled them, he labeled them some, like I say, with capital letters and some with small letters. And here are the wavelengths of these lines. I put the green lines in green and the blue lines in blue. Clever, right? And here are the elements that you can identify from these lines. Here's iron, one of the great hydrogen lines, more iron, more hydrogen, more iron, calcium, more calcium, iron, okay, nickel. Okay. And so all of a sudden we're beginning to analyze the chemical composition of the sun. It wouldn't be long before, as the spectra was studied more and more, very interesting, during the great eclipse of 1868, when we had the chromosphere, not the photosphere, but now this is the chromosphere. This is the burning hot gas that's above the atmosphere of the sun, okay? Here, they were able to, Janssen and Lochner were able to take a spectra of the chromosphere, and this is a burning gas. So this is an emission spectra, okay? This is white light coming out. You can see it's white, you can see it's a gray light. But when you analyze that light, what they found was lines, emission lines that they did not recognize. They found a very, very bright yellow line. Well, isn't that a dead giveaway to the two lines of sodium? Okay, and that's what they thought it was. But in careful analysis, drawing these lines very, very carefully, measuring as carefully as they could the wavelength that this line would have given its position in the spectra, it was not one of the two sodium lines. It was a line that was unknown. It was a yellow line that had never been seen in all the catalogs of all the spectra that they had in 1868. Janssen and Lochner discovered a new element. They didn't discover it in the chemistry lab. They discovered it in the spectra of the sun. Naturally, they called this element after the sun. It was the sun element. They called it helium. It was finally discovered in the lab in 1895, when the great researches on radioactivity began with the Curies, and uranium began to be looked at very, very carefully. And chemically, one was able to release from the chemical ore helium gas. And that's where that spectra was finally identified on Earth. But it took, what, 30 years of knowing that this element existed, but the only place where it existed, it seemed, was in the sun, not on the Earth. So you can begin to see the power of spectra and what can be discovered by the analysis of light. Norman Lochner is a very interesting fellow. He's the one who, among other things, founded the great magazine Nature in this same, I think in 1869. He founded the great journal Nature, which of course still exists today, one of the most prestigious journals in the world, still today. I've heard it quoted many, many times over the last few months about the pandemic research, that the articles that are coming out of Nature. Anyway, here's the founder of it. And if you got a chance to watch the biography video Father Secchi, he's actually mentioned there. When we get to Father Secchi, I'll mention the connection between Lochner and Secchi. They were, as you can see, they were contemporaries. But the discovery of helium. Okay, I think we have another chat. Okay, not sure what I'm reading here. All right. Sorry, someone is saying they can't see my whole screen. That I don't understand. I don't know. That's probably something on your side. I apologize for that, but I don't think it's on my side. Okay. So here is the full Fraunhofer spectrum in modern form. And you can see so many dark lines. Some of them are quite broad. Some of these colors are being absorbed in a whole broad nature of their wavelengths. And this, by the way, is a picture from Astronomy Picture of the Day. And you can see, again, that the brightest part of that spectrum, the kind of the brightest light, is in that yellow greenish area. And this is the absorption spectrum of the surface of the sun. All the various complex elements of the sun are absorbing these particular wavelengths. A lot of absorption is going on. Most of the light is coming through. Our sunlight is quite white light. Enough of all these colors are coming through for it to be white light. But when you look at it with this kind of care, a lot of colors are missing. And still to this day, there are some of these dark lines that we do not know why they're there. We do not know what is going on. It is not an element. It's not a simple element that when you just excite the element and make it glow, you will get that particular line as a emission spectra. Turns out that some of these lines now have been identified through quantum mechanics when various more common atoms, particularly oxygen, I know is a good example, when it gets into a very strange excited state and it moves from one energy level down to another, it will give off this very strange light that's unique to that particular quantum state and is not seen otherwise. And so when oxygen can get into that strange state, it has the ability then to absorb that amount of energy and will create this darkness in the spectrum. So you can see this is a whole science in itself, is the study of the sun spectra. Because the more we learn about the sun spectra, the more we can learn about stellar spectra. And that's where we go next. Okay. It took a while before people could make a spectra of a star. Stars are not bright, not compared to the sun. It's one thing to send sunlight through a prism. It's another thing just to isolate a star, to send that light through us. And remember, if you're going to send it through a prism, you're going to spread it out. So every single color is much dimmer than the concentrated white light. Very, very difficult engineering feat of the glass that you need. And the instruments that you need to spread this out so that you can still see it, see what that spectra is. Not surprisingly, therefore, the first spectra that was done was for very bright stars. And here is two of the earliest spectra for Aldebaran and Rigel, two of the brightest stars in the sky. And again, this is before photography. Even though there were cameras here in 1862, the light was much too dim to photograph this stuff. This had to be drawn by hand, by looking through the telescope, patiently sitting there, taking measurements of the wavelengths and producing these lines like this. Tremendous amount of work. And this was pioneered by two men. One, William Huggins, an amateur, rich man, a man of independent wealth who had a great interest in astronomy and took up the study of cell spectra as his mission. And as it turns out, the story goes, is literally his next door neighbor, one fancy house down out in the country, was a chemist at Cambridge by the name of William Miller. And he asked Miller to help him with this whole project of trying to unearth, trying to create the spectra of a star. And so they worked together for years, and they were the first ones to develop the early techniques of being able to even see the spectra of the dim light of a star. And it turns out, not surprising, that these were absorption spectra. That is, you're looking at the white light of Orion, you're looking at the white light of Rigel. Yes, it is a white light, but when you look at its spectrum, you see the dark lines just like you see the dark lines in the sun. Not exactly the same lines, no, by no means. Different stars now are going to have different absorption spectra. They're telling us something different, of the chemical composition of these stars. They're telling us something about the different temperatures of these stars, right? Because if you model that, the brightness overall by trying to find a continuous line, what temperature would create that continuous line of emissions? You can get a measure of the temperature of the star. So all this was in the early days of, first of all, just getting the spectrum of a star, dark lines or not. But the man who really needs the credit for making this into a science is Father Angelo Secchi in Rome. Very interesting guy. He is a Jesuit priest, and he joined the observatory in Rome as a very young man. And if you know anything about the history of Italy, you know, with the unification of the country, tremendous backlash against the clergy formed. People were sick and tired of the clergy running the country for hundreds of years. And so the clergy really, at some point, it got so bad in 1850, while he was a very young person in the College of Rome. He taught math, he taught philosophy. I think he did a little bit of work maybe in the observatory, not much. The Jesuits were run out of Rome. The new government who came in threw them out. In 1848, with the great, the great era of revolution throughout Europe. And he spent a year in England, and interestingly enough, he spent the second year in Washington, D.C. He actually taught in Georgetown. He taught math and physics in Georgetown. He was trained as a physicist in the Jesuit college, and it's there where he met the director of the observatory of the Naval Observatory in Washington, and began to work with him. And this is where he learned a lot of the real detailed techniques of astronomy. He actually learned it in his year in Washington, working with the Naval Observatory. They became lifelong friends. The director of the Naval Observatory with Secchi, and there's tremendous correspondence between them over the years. As 2 years later, he was able to go back to Rome. Things quieted down enough where the Jesuits were at least allowed to go back to Rome. But by then, the new government basically, what would be the word, nationalized everything that the clergy owned. I think everything but the Vatican itself was taken away from the Catholic Church. Again, in this tremendous backlash of being sick and tired of being run by them for so long. So the college was taken over. The great Roman college was taken over by the state, and the observatory was. Oh no! I'm sorry. I ran ahead of myself. So he goes back in 1850, and with his great knowledge coming from his work with the Naval Observatory, they put him in charge of the observatory. And there he spends the rest of his life from 1850 to 1878. In 1873, the final hammer comes down, and the Papal States, I think, are completely destroyed, and the whole country is nationalized and secularized under one unified Italian government. And one of the things that they did was they took over everything that literally the church owned, I think, except for maybe the Vatican itself, and particularly the college and the observatory. Well, story goes that Secchi objected to this. He said, wait a minute, I've been running this thing, for 20 years. You're not going to take this thing away from me. He was such an important astronomer, given the work that I'll describe in a moment. He was world famous astronomer, a leader in his field on stellar spectroscopy, that the new Italian government backed off. It's the one place where they backed off. and spin was applied. Oh no, Father Secchi, we never meant that you were not going to be the director of the observatory. Of course, you're going to stay in charge of the observatory. We'd be honored. And so, yes, he stayed in charge from 1873 until he died in 1878. The proof of the pudding is in 1878 they took everything away. As soon as Secchi died, they took all the great instruments away and dispersed them, with in other observatories around Italy, just to show again that the priests weren't going to own and control everything. But while Secchi was alive, no, they were not going to mess with this guy. So what Secchi began to do, he took in his life 4,000 stellar spectra. He invented a bunch of new instruments, improving on the work of Lochner and Janssen. On Huygens and Miller, on creating spectra. He pioneered the engineering, the optics of this as a physicist, and he broke up spectra into 4 categories. The first one was Sirius-like, brightest stars, Sirius being the brightest star. So there was a Sirian type spectra, very, very white light, very, very few dark lines. Then there was the solar spectrum. Spectra like the sun, many, many dark lines. Capella, Arcturus, good example of stars that has spectra very similar to our sun. Then what he called the red spectra, the red type star. The bands were much broader. The lines weren't as thick. More colors were able to show before black lines broke them up. Betelgeuse is a good example of a cool star which has this kind of spectra. And then finally, he just called it the fourth spectra, which was even cooler still, where there were actually very few dark lines at all. Very few and far between. It was mostly just a continuous spectra. And these are the coolest stars of all. This is the beginning of the classification of stellar spectra and why, what these different kinds of spectra were telling us about the sun. And this all comes from Angelo Secchi. So if you haven't taken a look at that biography video, it's not very long, 16 minutes, I think. It's very, very interesting. Tells more about his background, more of his other work. He did work in oceanography and geophysics. Very, very interesting guy. A very important astronomer in the history of astronomy. Besides, by the way, being such a great astronomer and well known throughout the world, he was also a very, very important figure in Italy. And this is another reason why the Italian government dare not mess with him. It was one thing to throw out the priests. It was one thing, to get rid of the cardinals. No, you don't touch Father Secchi. Okay, he's us. He belongs to us. He is our scientist. He is our great Galileo. You don't mess with him. And so that's why, one of the reasons why he was able to continue on with his work. It is interesting that you'll see in the bio that a lot of his work was suppressed in other parts of Europe, particularly in England. And that was done, apparently, I did not know this until I saw the video. I did not catch this in my research, by Lochner, who was the one who started the journal. He again was, working very much in the same area as solar spectra, and was jealous and felt that Secchi was overshadowing his work. And so he apparently refused to allow any of Secchi's articles to be published in Nature, which was at the time the most important organ for this kind of research. And this is why Secchi went for a long time unrecognized in other countries, particularly in Britain. So that was an interesting sidelight there about Lochner in the beginning of the journal Nature. So what's the next thing? Once you began looking at stars, well, we want to go to Herschel's nebula, right? What are the spectra of nebula? And certainly here, the great Andromeda Nebula, again, not known yet, is just the Andromeda Nebula. They took a look at the spectra, and sure enough, it was an absorption spectra. Okay, it had all the dark lines. This was not a glowing gas. This was a white light. Yes, they all look white. They all look white grayish, but this was mostly all the colors coming at you at once, with many, many of these dark lines, just like the sun, just like the stars. Could this possibly be just an enormous aggregate of stars? Certainly we see some nebula We can resolve those into stars. They're close enough, and the telescopes are powerful enough, right, with 2-3 generations beyond Herschel now. Many nebula can be resolved into a great cluster of stars. Can't be done yet with Andromeda, but that the spectra tells us that what we're looking at here is a collection of stars. How far away is this thing? Again, the power of the analysis of looking at the spectrum of light coming from these different sources. And here we have the Cat's Eye Nebula in Draco, discovered, remember, by Huygens. And this spectra was first analyzed by Huygens. He's the one who gets credit for this, and he wrote this in a popular. And he was an amateur, but still a very a very professional amateur astronomer, a brilliant astronomer in the area of spectra. And he writes this in a popular magazine. So you'd be surprised. It's not exactly what you'd expect from a dry science magazine, journal article. He says, on the evening of the 29th of August, 1864, I directed the telescope for the first time to the planetary nebula in Draco, popularly known as the Cat's Eye. The reader may now be able to picture to himself, to some extent, the feeling of excited suspense mingled with the degree of awe with which, after a few moments of hesitation, I put my eye to the spectroscope. Was I not about to look into the secret place of creation? I looked into the spectroscope. No spectrum as I expected, a single bright line only. At first, I suspected some displacement of the prism, and I was looking simply at the reflection of the illuminated slit from one of its faces. I thought for scarcely a moment that the true interpretation flashed upon me. The light of the nebula was monochromatic, and so unlike any other light I had yet subjected to prismatic examination, it could not be extended out to form a complete spectrum. The riddle of this nebula was solved. The answer, which had come to us in the light itself, read, not an aggregation of stars, but a luminous gas. And so here we have the beginning of a tool to separate Herschel's great question. Are all nebula the same? Are they all what they seem to be when you can resolve them into many myriads, millions, perhaps billions of stars? Huygens says no. Here, for the first time, and it's the Cat's Eye Nebula that is first discovered, that he has a monochromatic emission spectra. This is a hot gas which is glowing, just like the hydrogen in the lab. And so a remarkable discovery of the emission spectra, and beginning to catalog the different spectra of the nebula as this technology developed. Remember, it's one thing to take the spectra of a star like Vega. It's another thing to take a spectra of these guys that can only be seen in a telescope, the Cat's Eye Nebula. The light is so dim. You want to take this incredibly dim light and then spread it out, make it even dimmer, color for color, and you're supposed to see what you're looking, the technology here to do this, before our ability to magnify light was really remarkable. These early pioneers. He got so carried away with his one color that, sure enough, no, I don't recognize this color. I've never seen this emission band before. This must be a new element. Well, what would you call a new element that comes from the nebula? He called it Nebulium. Just like helium, he thought he invented a new. And here's the spectra of the Cat's Eye Nebula. You can see Draco here. This is spectra, and this is that one bright line that he saw, the first line that he saw. He eventually saw other lines, dimmer lines, and you can see them marked. Here's a hydrogen line. Here's the great Fraunhofer line of F. Here's a barium line. Here's a magnesium line, and here's his N line. Okay, so his line for Nebulium. No, there is no Nebulium, guys. You won't find it in the periodic table. Turns out that this was one of the first places in 1924. One of the quantum physicists were able to identify this line as being given off in a very special way by, I believe, by the element oxygen. It gets into a very strange quantum state and it'll give off this particular color. It's kind of a greenish color. So it is not a new element. But here's beautiful pictures down here. These are pictures of the Cat's-Eye Nebula, again, in different wavelengths, right? Looking at invisible light and infrared light and ultraviolet light. Tells us different things, seeing the different brightnesses coming from different parts of the spectrum. Okay, more discoveries to finish up. Huggins again. Huggins, guys, is one of the last of the great amateur astronomers. He and his wife, Mary, tremendous team, did so much work in spectra, both stellar spectra and in nebula spectra, and here even taking the spectra of comets. Mary, again, was not trained in any way, very much like Caroline Herschel, learned from her husband, became his right-hand man, was his only assistant. They worked together alone with their private telescope. They had the money to do such things. And it's amazing to read their journals. They would work like, when it got dark, 6, 7 o'clock, they would work, and 11, 12 o'clock, they would then knock off for the night and go to sleep. They worked, very English, very proper. They worked during some hours, and that was it. But what they were able to discover over the years was really quite remarkable. Mary and Huggins. They're a couple of Mary is one of my favorite people to read about her. But anyway, no time for that. But in 1867, he took the spectra of a comet. And what he found here was there was both an absorption spectra and an emission spectra in the same spectra. Sure enough, the absorption spectra was sunlight. Okay, what the comet was doing was simply reflecting off the light of the sun. But the emission spectra was something else. This was a glowing gas. This was the comet itself. As it got hot, as it got close to the sun, it began to glow, and it gave off its own light. And he was actually able to identify hydrocarbons. By 1867, the chemists were beginning to develop the spectra in the lab of all kinds of materials, compounds and even organic materials. And he was able to identify a hydrocarbon emission spectrum in this comet. So quite remarkable that we started to get these kinds of elements out in space. So to wrap up, I said that this presentation would bring you to literally to the threshold of modern astronomy, and I hope you can see that this really is a place now where we're beginning to look at information, particularly in the area of spectra, that was completely unimagined, by people like Herschel. And the great developments there, if I tried to summarize them, was, first of all, telescopes were getting larger and larger, more and more powerful, finally moving into mirrors, the great reflectors. And for there, with the larger telescopes, you could do the orbital motion of the binary stars, seeing the binary stars, the true binaries. And remember, from the binary stars, you can calculate the mass of stars. Remember how we were able to calculate the mass of Jupiter by watching the moon of Io? Well, it's the same thing. Here we have two stars which are revolving around each other. You can think of one as the central body and one as the satellite. And you can do exactly the same math, and you can calculate the mass of both stars. You can't calculate the mass by looking at the motion of an individual star, okay? But when the stars are revolving around each other, you can use that math of Kepler's laws and Newton's law of gravity to calculate the mass of stars. So this is where the first mass of stars were found, in the double stars. Very important area of research. Larger telescopes, of course, also expanded our ability to find parallax. And with parallax, we were able to find the distance of further and further away stars. And where distance and knowing proper motion of the star by the big telescopes, we can start to measure more and more that traverse speed of the stars. How fast are they moving across our field of view? So all this was done with just the larger telescopes. And with distance and apparent brightness, okay, going. Once you know the distance and we have this apparent brightness scale that we can measure reliably, um, we can get the absolute magnitude and start talking about the true luminosity of stars compared to obviously the most important unit that we could use, standard that we could use, the sun itself. Is this star 10 times brighter than the sun? Is it 1/2 as bright? We could begin to do that here once you know the distance of stars and you have the reliable measure of its apparent magnitude. Spectroscope, as we've seen, the stellar spectra, give us the chemical composition of stars. It'll give us the surface temperature of the stars, again, by matching the overall spectra to those theoretical curves, those so-called black body curves of what the spectra would look like for just a glowing hot body. If you can compare that, find the hot body which most closely matches the spectra of your star. That would then be the temperature of the photosphere of the star. And finally, something that we did not get a chance to talk about, which is the Doppler shift. Again, coming from the spectra, looking at your spectral lines, if you see them shifted from where they actually are in the lab, that means that this star is moving away from us or moving towards us at a very great speed. And you can actually measure that speed through the Doppler shift. So the proper motion gives us how far things are going across our vision. The Doppler shift tells us how fast the star is moving directly away from us or directly towards us. For the first time, we have 3 dimensions. We have depth perception in the sky, and it came from a very unlikely place. It comes from the Doppler shift of spectra. Finally, we get the 3-dimensional picture of the stars. And so if you know how fast it's going across your vision and how fast it's going towards you, away from you, you can then easily compute the true real distance and the true real direction of the stars. And we can really measure how the stars are moving, how fast they're moving, where they're going, etc. And of course, not only can we do that for the stars, but we can do that for the nebula. And once we discover that nebula are moving, that the nebula are moving, in fact, away from us. And once we can figure out that the nebula are island universes millions of light years away, and they're moving away from us because of the Doppler shift, we have an expanding universe. And where does that expanding universe come from? How did it start? We have the Big Bang. So you see where we go. And the other great instrument that comes online here during this time is the camera. And the camera, again, opens up a whole new window, a whole new ability to do things that could never be contemplated before. Just 2 of them. One will be just a catalog of photographic plates, having a record of what the sky looked like, and having an historical record. You could go back, not have to compare the observations of Ptolemy and Hipparchus and in Tycho, what they wrote down, but you can actually look at the photographic plate. Take a look at the photographic plate of 4 years ago compared to now. Put the 2 plates side by side. Put the 2 plates on top of each other, okay? And blink them back and forth to see if there's any change, any motion. One of the early developments of photography is just to have a record of what the sky looked like, or whatever you were photographing, the planet, the star, the nebula, and how it would change over time. And finally, the ability to have long exposures. If you could track that camera to a telescope and have the telescope stay with that part of the sky, have it move as the sky moves, as the Earth turns, have that field of vision stay fixed for many, many minutes, for many, many hours, and now with the Hubble, for many, many days at a time, and let that light accumulate and accumulate and accumulate on your photographic plate. All of a sudden, you will see things that you would never, never see, no matter how long you stared at that part of the sky, you would never see what the photographic plate can see because of the long exposure times. And all of a sudden, we're beginning to look at objects so much further away from us than was ever even conceived. So the beginning of the so-called new astronomy. That was a famous phrase coined by Huggins himself. Here's a nice example of that deep sky observations. Here's a great famous picture of Hubble. Here up in the corner is what this piece of the sky looks like to the naked eye. Very, very tiny piece of the sky. It's only 150 arc seconds on a side, and there's nothing there. To the naked eye, it's a little tiny little dark patch. You set the Hubble on it, and you let the Hubble watch and watch and watch in the same place for hours and hours, and this is what you see. What you see is not just remarkable that all of a sudden you see things that you can't see with your naked eye. No, that's not what's amazing. What's amazing is the only two things here, there are only two things in this field which are stars. Only these two, I think the two things which kind of glow, which kind of have a sparkle to them, a refraction element to them. Anyway, there are only two elements here. Do I have it in the slide? Yeah, there's only a few actual stars in the Milky Way in this picture. There are 3,000 objects in this picture. Only 2 or 3 of them are stars in the Milky Way. The rest of them are all galaxies. And that's what the Hubble can see, thanks to not only its great camera, its great field of view outside the atmosphere of the Earth, but it's the camera that's able to do this. So, to wrap up, were there open questions at the end of the 19th century? Sure, there are always open questions. Our open questions are, what is dark energy? What is dark matter? How did the Big Bang actually start? What did the universe look like in the first few seconds? Where is the universe going? How will it end? Will it ever end? There are many, many. Why is the universe expanding at an increasing rate? I get that it's expanding, but don't you think it would start to be slowing down by now? You're telling me that the universe is expanding at an increasing rate? Many, many open questions that we have today in 2020. What were some of the open questions that the astronomers were left with after their great work with the spectroscope and the camera? Well, are all nebula of stars, are they all just clusters of stars? Are they all, do some of them, are these radiant clouds? What's going on in these radiant clouds? Or is there something else? Is there something that we're not even catching about what these nebula are? There are so many different types of nebula. And do the nebula play some kind of role, particularly the gaseous nebula, the ones that have that emission spectra? Could that possibly be the nursery of where stars are formed? And they start from these clouds and begin to form stars? Are we actually looking perhaps at young stars? Does the Milky Way system, what we see, is that the entire universe? Or are some of these nebula actually outside of our local system? Are there in fact these island universes that Herschel talked about? Some of these nebula are Milky Ways in themselves, great aggregates of stars which are incredible distance away from us, where there's a vast distance of nothingness between us and that island universe. Is that possible? Is that so? Can we lock that down? Can we say one way or the other? Is that true or is that not true? Can we finally show that all the nebula that we can see are relatively close to us? Or can we finally show that there are some nebula that are very, very, very far away, way beyond the measure of any star that we know of? Is that possible? And finally, from that question, what is the size of the universe? Is it finite? Is it infinite? Does it make any sense to ask that question? What can we talk about the entire universe as a whole? Okay, guys, so that is our presentation. I will leave this for you. This is just a photo essay I put together of the development of photography. You can just go through the slides and see the dates and taking pictures. First picture of the moon. Here's the picture of the sunspots. Here's the first photo of a star. Not surprisingly, it's Vega, a very, very bright star. The first photograph we could take of a star, and on they go. It's a very interesting little photo essay I put together about the development of photography. By the way, the word photography was coined by John Herschel, of all people, the son of William. Okay, so that is it. That is our course. I hope you enjoyed it. Let me go ahead and get out of share and let me unmute everybody. Where is everybody? Everybody's here. Okay, you're all unmuted. by magic. You may be muted yourself, but you're all unmuted. So I hope you enjoyed the course, and I look forward. We will be doing something in the fall. I'm not sure what. Stay tuned. You'll be getting an email. I will certainly send you guys an email when I finally figure out what it is. I have all your names. Heather certainly will be getting out a catalog, but I'll send out something to you guys early, let you know what I'm up to. All right. So if there are any questions before we finish for the day and the term.
Terrific.
I have a question.
Yes, Frank, a question.
Yeah, I'm curious about the reaction of, and I will just use the word church. I don't necessarily mean Catholic Church, but that, of course, is part of it. What's the reaction from religious people regarding the age of the universe, regarding the size of it, or even thoughts that there might be people or creatures on other planets? I mean,
well, Frank, I am the product of a very strict Catholic education. I was born and raised in the working class Catholic Bronx, and there was never a hint of a conflict between the religion, my religion, and science. Quite the opposite. Science was always very powerfully promoted. It gave me my love of science. So the church today takes the advice of Galileo. The Catholic Church takes the advice of Galileo, that if religion seems to be conflicting with what we know is true about science, for God's sake, figure out a different way to interpret what you thought was true. For God's sake, stop hitting your head against the wall. The sky is not green, no matter what Plato said. So,
okay.
So
I was brought up in proximity. I'm sorry. I was brought up sort of in proximity with evangelical thinking. And they had, you get all sorts of weird things.
I know.
Coming through. And I mean, Darwin in particular.
I know.
Huge problems with that.
I know. Tremendous.
Anyway,
I tell you,
big subject, and I'm just curious.
Yeah, no, it is a good subject, Frank. And if you take a look at that video of Cherchy's life, these are all priests talking. These are all members of the observatory of Rome. These are, and they're talking about his research into cell structure. And these are all modern scientists today. There is the Big Bang. Pope Paul the 12th, Pope Pius the 12th, he really welcomed the Big Bang. This was proof of God, as far as he was concerned. The Big Bang proved that God created the universe. So evolution. There was never a conflict in my very strict working class Catholic upbringing between science and religion. The evangelicals, I don't know why they need to stick to this literal interpretation of a book, which is so old. Why they would want to stay with a book which is so old. Again, as Galileo said, the book is not about how the heavens go. It's about how to go to heaven. It's not about how the heavens go. Why don't you read the book about what it's about, as opposed to what, Don't get me started.
Okay.
All right, guys. It was a great pleasure. You guys were a great group, and look forward to seeing some of you back in the fall. Stay healthy. Stay well, everybody.
You too.
Thank you so much, Peter.
Okay.
Thanks a million.
Yeah,
Thank you very much.
It was a great pleasure. You guys are great. Bye-bye.
You are too, Peter. Thank you.
Okay, thank you.
Bye-bye.
Bye-bye.